Yeah. You have to choose the, what's the name? Yeah. The man will introduce you.
So perhaps I will start. It's so I today I want to speak about combinatorial zeta function, and I chose to speak about people in the audience who's yeah.
Which one?
Yeah.
Yes,
yes. So, I chose to speak about combinatorial zeta function because it's a topic which interlaces with research interests of several people in the audience. So I wanted to point towards the connections with different subjects. So. Work. So let's start. So a graph is a graph, and we take it with an arbitrary orientation. And just for formal reasons, perhaps I will denote the edges of the graph E, and then the chosen orientation AE, and its inverse of the edge, inverse orientation, I will denote AE inverse. Just a formal notation, and then the basic object is prime reduced cycle, or one can take, say, prime reduced closed walk. Okay, and it is just a sequence of vertex, directed edge, blah blah, which ends in the same vertex, and the directed edges. So this AIs are just directed edges, but you can go also against the orientation of the edge. But it's good to have the fixed orientation, reference orientation. And so it's reduced because you cannot go there and back immediately. AI is not equal to AI plus 1 inverse. And it's prime. It means that it's not non-trivial power of smaller cycle. All right. So and then there are two main functions in this. So this is a basic notion in this area, and it is standard somehow. It is. I hope you recognize it. So Ihara. So sometimes this is called prime. Reduced always cycle is called sometimes a closed walk.
Do you allow multiple edges? So can you, for instance, go from
Yes. Not immediately. So you can never go immediately back.
You can repeat the same edges.
But you can repeat in the same walk. You can repeat the same edges. So you can. It's really a mess. But you cannot go there and back on the same edge immediately.
But if you had two parallel edges, you could go out on one and back on the other.
Yes, but that we don't have, because you have orientation of a graph. You have a simple graph.
Oh, it's a simple
and yeah.
It's a simple
Yeah.
Okay.
You mean every edge can be labeled two directions?
You fix, that's why somehow to avoid this, I take simple graph, I fix orientation, it's a reference orientation.
Every edge just one orientation.
It's a fixed orientation, but in the walk you can go against that orientation, but that you record it as AE minus 2 minus 1.
So the orientation plays no role.
It's a reference, well, it's not true, it's a formal reference.
But it's irrelevant which you denote AE and which you denote
Yes,
AE.
that's right. So the two main functions are Ihara-Selberg function, which is defined like that, where the product is overall prime reduced cycles, and the zeta function is.
Oh, sorry, wait a second. So U's are indeterminates.
U is the yes.
You have a collection of U's?
One, here it's just one, so X, single variable.
Oh, it's a single variable?
Yes,
The weight
yes.
for each edge?
No, it's a weight for each cycle? No.
It's a size of the number of directed edges in the number of steps in the prime reduced cycle.
Oh, I see. But you could, there would be no harm if you put for
Yes,
each
different
direct-
variable and
for
then
each
product of,
directed
yeah,
edge.
yeah. But it's defined, yeah.
I like multivariable.
What?
You like multivariable.
I do, wherever.
Yes,
wherever
yes,
it's
yes, yes,
natural,
yes,
I
yes.
do it.
Multivariable, yeah.
So I'm just trying to say, it
Yes,
is
yes,
even
yes, yes.
natural, and it's even natural that you have independent variables
It
in
will
two orientations of the same edge?
That does so. It usually, indeed, you get a different variable for each undirected edge, and that variable you associate with both
Oh, you should say
orientations.
one variable
Yeah.
with both
Yeah.
orientations.
That's well, I guess.
And the graph letters prime reduced. The letter below is a product. What is this letter?
This gamma is gamma. It's the length of gamma.
Not W.
Is the graph allowed to be infinite?
The graph is finite, but the product is
Very-
infinite.
Okay, yeah.
Sorry.
U and W are the same.
No, there is no doubt.
Well, there is a U which looks like a W, but it's indeed a U.
Yeah, sorry. So, I'm horrible in this, right? And there will be problem with K. I realize that K I write in a different way. Anyway, so this product is infinite. Even for small graphs, this is an infinite product, right? Because you can, for instance, this prime reduced cycles. That is the nice thing on it, that it's non-trivial even for simple things. So let me take pathological example, just two loops, all right. Then let's say this is loop A, this is loop B. Let's fix this kind of orientation. Then A to the N, B is a prime reduced cycle, right? And it is, N can be arbitrary.
Is it something like the zeta function, the traditional zeta function that you can write as a product over primes, or as a sum of?
That is the motivation for the name, I'm sure.
Can you remind us the traditional zeta function? I can't remember.
Let's maybe after the lecture, perhaps we can. If just to get somewhere. Okay, so there are two basic things which which I want to speak about. It's Bus theorem and McMahon-Master theorem. So Bus theorem is that the Ihara-Selberg function is a determinant, and here this, sorry for this, you put U to all the entries of the matrix, or you can imagine that U is the diagonal matrix where U is any entry of the diagonal, each entry of the diagonal. So that's one thing. Where what is T? T is matrix of transitions between edges, all right? So you have between directed edges. So you have if A and A prime are in this set, so set of all possible orientations of edges, and A is different than A inverse. Remember that you cannot go immediately back, so there is no transition between A and A inverse. So if the tail of one is the beginning of the other, you say that the A prime is 1, otherwise it's 0. Right? So in this theorem, you will have U there instead of 1. And then, so that is Bus theorem, and then second ingredient is McMahon-Master theorem, and it is basically interpretation of 1 over this thing. Right. So it is you can write it in this way, or I like to, so that is somehow that the coefficient of this monomial in this product is equal to the coefficient of the same term in the expansion of 1 over determinant, or you can understand it combinatorially. So let me, because this is the standard statement of McMahon-Master. Let me say, well, coming from discrete maths, I kind of prefer this one, and since it is less well known, let me explain it. So it says that 1 over determinant can be expanded in flows, all right? So what is this? Imagine that B is in the is V by V matrix of directed graph. So any matrix, you can look at it as a directed graph, where it's V by V, so its size of V is n, where this entry x, y corresponds to a directed edge, let's say from y to x, and the weight here, so this is, let's say, beta y x, beta y x. All right, the weight of the directed edge.
In our case, the indices of the matrix run over the edges, not over the indices.
Here in this interpretation, all this is the matter of interpretation. Here you look to the matrix in a different way than in the Bus theorem. In the Bus theorem, the indices were edges. Here the indices are vertices. All right, is the matter? Yes.
You said the product is infinite. How come Bus theorem seems to say it's a polynomial in here?
I think there's a -1 missing from somewhere.
It's no. It's the -1 is in the IUU definition.
The product is infinite, and nevertheless it's a polynomial.
There is there is your minus. It's infinite product, but that is basically that is the statement of the Bus theorem that basically the tail cancels. That is the why it's nice somehow. Okay, so let me, and that is the main difference between the Bus theorem, which actually was nicely explained by Foata and Zeilberger. I will explain it on the next slide. That the Bus theorem somehow looks at matrix as incidence matrix of transition between edges, and McMahon looks at it as somehow transitions between vertices which are directed edges. Okay, so what is this formulation? It is if you interpret matrix B as a matrix of weights of on directed edges of a directed graph, then 1 over determinant I minus B is sum over all flows. What is a flow? It's just it's an integer non-negative integer function which satisfies Kirchhoff law at each vertex. Okay, so circulation, non-negative integer circulation.
On edges.
Yeah, it's a function on edges. Sum over all flows. Beta f multi f. What is beta f? It's what you would expect. It's a product of overall directed edges of the digraph. Beta f to f, beta e to fe. Right? You take each edge as many times as it appears in the flow, and multi f is just product of binomial coefficients or multinomial coefficients.
It's really f, not something like absolute value or square, so it can be negative also.
F is f is flow, which is non-negative integer flow.
Flow is not an antisymmetric function.
No, it is non-negative integer which satisfies Kirchhoff law on each vertex.
Because you separately have
You have directed graph.
directions.
You have directed graph. Something gets in, something gets out, and you want that it's 0 at each. That sum of what gets in minus sum what goes out is 0.
So for each edge,
Can you have a non-zero flow on an arc in one direction and also on the same arc in the other direction?
Yeah, yeah. Here it is general matrix, so general digraph. It's not.
Yeah.
Now it's a general matrix, so it's not symmetric, or that doesn't need to be somehow underlying.
Usually it's in Chartier-Potin, it's some of them all rearrangement. So you mean flow is a rearrangement? No? I mean there is the same number of edges getting in, the same number of edges getting
No. Flow is a weight function. Flow is a function from directed edges to non-negative integers. flow.
Is it the same definition as in Cartier-Pointin, or you are changing the?
That is, so it's implicitly in Foata-Zeilberger,
They
but
define the flow, and then there is a subset of flow which are rearrangements.
so maybe it's different. So F is just function from directed edges to Z plus, such that for each vertex, sum Fe E equals V equals sum Fe E equals so these are some overall edges which starts at V, and this is some overall edges which end at V.
So you should, because if you want to be coherent with Cartier-Pointin definition, you should put rearrangement.
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 So
The
the
flow of it is, can be anything.
they call flow rearrangement.
No, they define flow. Flow, it's when the commutation relation between the letters are edges, and the two edges commute if and only if they have different origin. The concurrency relation is when they go one above it, and the flow arrangement is a subset of the flow.
Oh, okay. Oh, whatever. It's
You are going to make reference to this, and it should be better to say rearrangement instead of.
it's done already. It's so we called it flow in our paper, joint paper with Stavros Geroufalidis. Let's.
Flow is the usual term.
Yes, I agree, because I said to Fata that he make a wrong term to use the term flow for something.
You see, so we
Flow,
use it
flow.
correctly.
So, but I tried to change the definition, and
Yeah.
he said, no, don't do that.
Okay.
So maybe now I will argue with him and say,
Okay.
now we call flow what is flow.
It's and it appeared in Annalen, so there
Just
is
one
some
question.
reference.
Okay, so let's use this word now.
The multinomial coefficient at the bottom, is that product, is the stuff only over the outgoing edges
Yeah.
or all of them?
Outgoing, only outgoing edges. For each vertex, FV is some overall flow which goes out, and it's partitioned. It's useful. This was very useful in our analysis of Color-Jones function. This statement of and it somehow it has nice combinatorial meaning. These flows they are. So as I said, what I like the way Foata and Zeilberger connect these two, Bass and McMahon. It is they put it, so how they do it, they put it into Lyndon-Ward's machinery. All right, so what is Lyndon-Ward? It's if you take a finite linearly ordered alphabet, and then on all wards take lexicographic ordering. Then Lyndon-Ward is prime. It means that it's not non-trivial power of smaller word, and it's minimal in its cyclic rearrangements, minimal with lexicographic ordering. And then there is this kind of famous Lyndon.
I'm sorry, so a Linden word is,
It's a word with special properties.
I'm sorry, so initially you just think of it as
A word.
a word, it's not, you don't initially think of it cyclically.
No, it's a word with some properties.
Representant of the system.
It's prime, and it's somehow that's what it is. And you take it's defined as it is, so that Lyndon decomposition factorization theorem works. It is that any word, any non-empty word, can be uniquely written as unique decomposition into non-increasing Lyndon words.
What's the order on Linden words?
This
Or lexicographic?
lexicographic, sorry, lexicographic. All right, and now what he takes a matrix indexed by the alphabet, okay, and you can look at the matrix as the element Bij as a weight of transition between I and J, from I to J, right? And then, as I said before, if that matrix if X is interpreted as vertices of the digraph, then you get McMahon-Master theorem. Then that is a natural interpretation for McMahon-Master. And if X is taken as edges of the digraph, then that is a natural world for Bass theorem.
I'm sorry, so you're saying that these two theorems are trivial corollaries of Linden's theorem?
No. It's the machine. It's more complicated. The machinery which puts them together is this Linden world machinery. Here is the.
I'm a little. Well, maybe you're going to tell us.
Yeah.
About that. Okay.
So here is the statement, the theorem of Foata and Zeilberger. So you define some, here some elementary functions on with these notions, and basically what you have, what is important, you have a word, then it's a Linden word decomposition, then this is standard thing, this is from this you get from the Linden decomposition, and then a trick from which actually you get flows is that you kind of rearrange the letters of the word in non-decreasing order, and then you put the x1 below x1 prime and so on, and that is this, right? So somehow that would need some. So this theorem is not complicated. And then they prove that this equals this equals this equals this. That this includes both McMahon-Master and Bass. So Bass theorem is that this equals to this because you just take inverse and you get Bass.
Okay, slow down for a second.
Yeah.
So one side of Bass is the determinant, and the other side of Bass
is this product.
and B circ of L is just the weight.
It's product
Wait,
over
wait,
all.
wait.
Yeah.
Product over.
Or all Linden words. L
Okay,
is
the Linden word is a representative
of a reduced
a
prime
set-
reduced size. Yes,
reference
yes, yes, yes.
and McMahon-Master.
Is this last equality? That this 1 over determinant is this beta word, where beta word has to do with this non-decreasing rearrangement of your word.
Because that will somehow relate it to flows?
Yeah, and that it needs some explanation which I will not get into, but it's not, it's kind of elementary, I can say it.
X edges or vertices?
No, nothing like that. It's an abstract alphabet. It can be both edges, it can be either edges or vertices. It's an abstract setting.
So, but from this general result in two different interpretations.
You have an alphabet, X is alphabet, some finite linearly ordered set. X is linearly ordered set.
And then depending on how you specialize the interpretation,
Yes.
you'll get back
Yes.
or
Yes.
McMahon.
It depends. Transition matrix between vertices or transition matrix between edges.
That's right, yeah.
The
Yeah.
matrix are
Yeah.
completely different.
Yes, yes, yes.
And it is really the fact that you have some transition matrix which generates arbitrary closed loops, and the point is that you can decompose them into prime loops in a sense.
Yeah, yeah,
Arrange them
yeah.
as the product of primes.
Somehow, but
Like the integer.
yeah, yeah, and exactly, and you must make order in this. That is the intuition, but to prove something you need to make order, and the order is done by this machinery of Linden words. So that is somehow a mechanism that makes order
There is a
in this.
mechanism of prime decomposition also for knots, isn't it?
Yes, but I don't know whether there is any relation with it. So that is that's okay. So the first question is whether
I explained it.
yeah, no, I like so I like this. So there are a lot of proofs, of course, of McMahon-Master theorem, of Bass theorem. I like this approach because it puts them somehow together. I like that's what I want to. I want to look at them as two sides of the same coin somehow. So first question arrives. So there is.
I'm sorry, one more thing. You have one more equality here than you explained, right? I mean, you have four things that are equal,
I will not explain
What
because
is the
I will.
B deck? B deck is the product of B circs over the Linden decomposition.
Yes.
And so you won't explain that?
I will not go into the proof of this.
No,
It's,
but I want to know.
the same.
I'm not interested in the proof, but the statement. The statement states 3 equalities, and you only mentioned 2 of them. You didn't say anything about this B deck.
Yeah.
Is it useful?
And I will not say. I think I don't know whether I don't know. I don't know whether it's probably it is. So there is. So here comes I try to for on the next slides. Each slide should have some question. So here is the first. So there are actually several non-commutative versions of McMahon master theorem. Some are very useful. At least one is very useful. For instance, in a knot theory, I will speak about it in a minute. So what about Bass theorem? Is there somehow an analogous non-commutative version of Bass theorem? Can this approach using Lindon ward, this machinery somehow be put into this non-commutative context? That's I don't know. So here is first application of first connection with knot theory. There is a non-commutative McMahon master theorem. I will not even state it. It was proved by Garoufalidis, Tankle, and Doron Zeilberger. It actually was found. The statement was found by Tankle because he needed it. He needed it for an expression for Colored-Jones polynomial, and we used it with Stavros for the same thing. Then, Tankle and others have also a non-commutative kind of expression for Colored-Jones, but we have it. We have it also. So I will not even say what is Colored-Jones function. It's some generalization of Jones polynomial of knots. Okay, it's yeah, and we showed that it is the statement is technical, but it's not for purposes of this lecture. I don't need to say it exactly. It's an evaluation of something like 1 over quantum determinant of a matrix associated with knot diagram. Okay, so this in fact it's not really, so the evaluation is more complicated, and it's not 1 over determinant, but kind of something which we call fermionic expansion of Q determinant, which if Q is 1 equals to determinant, but for Q different than 1, it's not equal to Q determinant, but it's close to Q determinant. So
that Q equals -1 is determinant.
Q equal -1, it is you will get yeah, for Q equal to -1 it is permanent. That's right. I mean this statement. So here is the definition of quantum determinant. It's some overall permutation. Basically, -1 is replaced by -Q. Okay, and so it's here is a very question. I'm really very yes.
The A's are the matrix elements are the non-commutative.
Yes.
In the line.
Here it's anything. It can the matrix can be the entries can be commutative or commutative. They can commute or they don't need to. Here we use it for right quantum matrix.
So if they don't commute, this product has to be written in some specified form.
Yes, that's right, and that I omit here. So it can but anyway take.
In your application, they are commuting.
They are not commuting. In the here,
not even that.
No, it's a right quantum. It's really it's a Q determinant of a right quantum. So this B is a right quantum matrix.
It was having that rule you were telling me.
It's you have different rule for rows, different columns, and for any 2 by 2 submatrix there is a cross row, cross rule. That is somehow the... So the question is, can this be written as an integral, right? So there is a good price for it because in fact something like that is Color-Jones polynomial, and Color-Jones polynomial, Color-Jones function can be written as an integral in a very complicated, in a rather complicated way by Witten. It's so it is. So is there? But perhaps there is an easier way or more elementary way to write it as integral. So if 1 over Q determinant is an integral, then that would be another integral expression for Color-Jones function. So also in a later paper I showed that not Color-Jones function but normal Jones polynomial is a permanent. So and in fact for that I use R matrix Turayev description of Jones polynomial. So I expect that something like that may be true for all quantum not invariants. So again the same question, is permanent, and can you write permanent as integral?
Is it true maybe that for Q a root of unity A allows for the group of elements A allow for finite dimensional representations?
I don't know. Maybe we can discuss it after the lecture.
But Q root of unity is never special in your analysis.
No. Oh, no, it's not. It's we take a Q a variable as yeah. But it may be it's possible that that's a good specialization somehow. So so here is another relation. So I can write this. I can also destroy this nice device, but I can write the same function, this Color-Jones function, as in a very extremely strange way, and I can write this as formal power series whose coefficients are equal to defected Q chromatic function. I will speak about it later. Applied to linear combination of long chord diagrams constructed from flows on this on the reduced node diagram K. Okay, so here it should be node diagram. I take node diagram K. I take something. I take flows on it, whatever, and or one can look at it that from a node diagram one can get a set, a complicated set of flows, and from flows I get long chord diagram. Well, chord diagrams are just you have a cycle and there you have some chords, they can intersect, and long chord diagram is just that you break the cycle. So long chord diagrams are animals like this, right? So this guy can be written as in this way. So you take linear combinations of these animals, formal linear combinations, and you apply some chromatic operators, chromatic function to it, and you get Color-Jones function. So another question for the not theory colleague is, who is interested in weight systems, is whether there is some relation with weight systems expressions for the Color-Jones polynomial. And it's well, there are known relations of chromatic polynomial and chromatic kind of functions with weight systems of not invariants. There is something. There are these chromatic weight systems of Kmutov, Duzhin, Lado, and Loebl and Welsh, And so there is it doesn't need to be completely off, and there is other relation of Jones polynomial and chromatic polynomial. It's with Ian Moffat we constructed Kovanov homology for chromatic polynomial, which somehow is closely related to the Kovanov construction for Jones polynomial. So it's this Jones polynomial of knots and chromatic polynomial seems to be interlaced in many ways.
Kovanov was that scaling one. It's a bit special as a polynomial, isn't it? It's not. It was that not invariant, which is quite far from the other traditional ones.
Not so far. It's well, it's a longer story. Maybe we can. So the Jones polynomial is Euler characteristic of some chain complex, and if you take Poincaré polynomial, then that is he proved somehow that other stronger things than this Euler characteristic are not invariant. And, this it's very nice, very exciting, original. Yeah, in this, if you meant that it's new original approach, then yes, it is. So what are these Q chromatic functions and these things? So, well, let's take, so that's, it's a definition, it's my definition which I like. So let's define this function. Okay, so it's sum over, this should be S. Should be S, and it is a proper coloring of a graph by colors from 0 to k minus 1, right? So S is proper coloring. So if Q is 1, I take sum over our proper colorings of 1, which is just number of proper colorings of graph G by k colors, which is chromatic polynomial, right? But here I take, instead of 1, I take Q, and colors matter, right? It's colors are from 0 to k minus 1. And
just a small comment. People typically call Q the number of colors. E and Q was for the quantum
in physics,
parameter, so K is the number of colors. So
it's it's in physics. This Q state Potts model is Q is in Potts Q state Potts model, but it's.
But I would say this is a special case of the Potts model in a magnetic field, right?
Yes.
Because the Potts model, you have weights for
we will
same
get,
or different on edges, and then in a magnetic field means that every time a vertex is colored a particular color, it gets weight associated to that color. Now here you have a very, very special set of weights associated to the colors, namely 1, Q, Q squared, Q cubed, right?
Well, let's do it concretely.
So I don't quite see why that's natural, but
In our domain is natural.
in your domain it's natural.
The
Okay.
choice of a color, the choice of I, you put Q power I.
Okay.
So well, it's so this really appears. So I got to the definition because that's really in an attempt to understand or to re-say our complicated proof of the formula for color-Jones function. So this kind of popped out, and it turned out that it has beautiful properties. So well, for instance, well, it's a classical formula from this Q computing is that it's for complete graph. It is this expression. It's good to know. It is. So what is it? It is well. Everybody knows what is Q to the sum SV, where SV is from 0 to k minus 1 arbitrary without any condition, right? It's just this product of geometric series, but geometric summation. But if you have X, so for this thing, for complete, it means that you have only one condition, and it is that in this sum the terms are all different, right? then it's not clear a priori what to do, but there is a nice formula which involves these Q numbers which are defined in this way.
This is Q analog. Called Q analog, and that's Q.
So what is nice on this is that one can have this inclusion-exclusion formula. So there is for chromatic polynomial you have sum over all edges -1 to a k to the number of components, right? And instead of that you have this term here. So k to the number of components is nothing else than product over all components of the subset A of k, and here instead of k you have k in the base q to the w, right? And this naturally leads to the definition of q dichromate, which is just that as in a Tat polynomial or dichromate you replace -1 by x, right? And there is and this is very natural function. It's not difficult to show that it's basically Potts partition function with magnetic field. So it is so this guy. So let's take to each edge. Let's be multivariate. So let's put different variable on each edge. Then this guy is equal to sum overall function s from vertices to null 0 up to k minus 1, q to the sum sv, e to the I guess this z includes e. So that's for special z. Sorry, so that it's this. It goes via. I think z is 1 plus e. Well, whatever. So it goes via this Fortune-Castellane expression for the Potts.
Right. So this is.
And here, 1 minute. Let me finish. So here is just the standard definition of the energy of the Potts. So this function is really nothing. Is closely related to Potts partition function with. I heard that it's called variable magnetic field.
Right. So this is the usual, or I don't know how well known, but anyway, it's a Fortune-Castellane formula for Potts modulated magnetic field, which is fairly well known, but specialized to a particular type of magnetic field on the right-hand side, and therefore it gives a particular type of component weights on the left-hand side. This k to the base q to the w.
Can you comment on the fact
Yes.
that for generic magnetic fields, you do not have any analytic continuation in Q, even because they are too generic. But for this prescription, well, the way in which K enters in a few of these expressions is now analytic in K, isn't
Yes.
that the symbol?
Yes.
So
Yes.
for this prescription, you have a natural analytic continuation in the number of colors, which
That's
wasn't
true.
expected to me. If they asked me, what would you do with the magnetic field, I would have answered nothing.
Oh, no, there is a good analytic continuation for.
So in any case, that's what I would like to. That somehow I don't know all this thing. So that I wanted to ask whether this formula, well, it's not difficult to prove. So it's probably known, or would it be kind of interesting for the study of Potts? There is another, of course, you can. Specialize to Ising model, but then I heard that last week that there is something called Q Ising model, which looks or quantum Ising, which looks completely different. So somehow I would be curious to hear about these things. Why I am interested there? It's another aspect which I want to tell you about of this Q dichromate. And it is how strong it is. So as I demonstrate, on one hand, it's a kind of very natural function. It is just, let's say, Potts in magnetic field, variable magnetic field. But on the other hand, it may be quite powerful. So I conjecture that one can reconstruct a U polynomial of Loebl and Welsh from it. So it's not, should not be, it's not called polynomial, right? It has infinite, is it polynomial? But it has infinite number of variables, right?
It's only finitely many on any graph. So.
Okay, that's right, yes. So it has, it's a function of in infinitely many variables defined in this way, where basically what you get, what it is, which information you get. You specify the size of the edges you delete, and you specify partition of n when n is the number of vertices, and it gives you number of subsets of edges, so that if you delete them, the connected components of the rest define that partition. Okay, it's a powerful information somehow. It's called I guess universal. It's probably so far as I know is the most powerful function defined on graphs somehow, no? Or generalization of that
Wait a minute,
polynomial.
is it this just, can't I just say this as, I write out the usual sum over a's, and then instead of giving a q, well, what I call a q, what you call a k, for each connected component, I have different variables depending on the number of vertices in the connected component. Is that right? I mean, the
Yeah.
x k, well, x,
That
x, j
variable,
index is a component with j vertices. Right.
I see what you meant when you said that you can do the analytic continuation even for arbitrary magnetic field. That's kind of a spectral decomposition of xk as sum of a lambda over to the k ak. If you do this, then the lambda is equivalent to the magnetic field, and the number of times you need is the number of colors you need in order to do this spectral decomposition of the size wave.
Okay.
And this is the case.
I'm not
in
sure
which
what
it
you're
is
saying, but we can talk
Anyway.
about that later. But I just wanted to say that, I mean, the most general thing that you could imagine is you choose A's, right? Sum over A's. That partitions the graph into connected components somehow. And then you get some weight, W, for each connected component.
different for, yeah.
Right? And usually that will be of the form product of edge weights, and then other stuff depending on the component. A special case of that is it depends only on the vertex set of the component. One special case of that is it depends only on the size of the vertex set of the component. Potts in a magnetic field is a different special case where the weight of a component depends on the magnetic fields and on.
So that somehow on one hand it's
There's a lot of
easy,
different special cases.
on one hand it's easy to see that these spots in magnetic field, you can get it from U polynomial, it's universal, it's U because universal, this Stanley symmetric function generalization of bad chromatic polynomial and so on, it's equivalent to U. So it is, so far it's universal, the strongest we have. But
It's G minus A.
You take edges of A from the graph G.
And
So
then all the vertices.
disconnect two connectivity components.
You could equally well write it as G restricted. G.
Okay. But let me get, because that,
I mean, you leave in the vertices or not?
yeah, you leave vertices, you delete edges, so it breaks into connected components. So so I bravely conjecture that this universal is not stronger than this Potts, this Q dichromate, Potts with magnetic field. And in fact, this conjecture would follow from the following conjecture, which I like, which is conjecture about partitions of numbers. And it is the following. So you have, take n, finite number, take partitions of n, you have finite number of taus, and for each partition, to each partition you associate an infinite dimensional vector, okay, and a series of polynomials. So it's a vector of polynomials indexed by 0, 1, 100 million, blah, blah, where C tau y is product of these of these polynomials in Q. Okay, so each entry C tau y is a polynomial in Q. Okay, and so each end, so you have this. You can look at it as infinite columns. You have finite number. Let me finish. You have finite number of them, and then the conjecture is that they seemingly they have nothing to do with each other.
I don't understand the definition. What does the dot 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 mean?
This is all numbers, all integer, all positive
dot,
integer.
Dot in the product.
Oh, y minus 1, y minus 2 up to 0. Y minus 1, y minus 2 up to 0.
Okay.
So
Because y is an integer.
yeah.
Y is an integer. Okay, sorry.
So then the conjecture is simply that only trivial rational linear combination of these vectors, of these infinite dimensional vectors, is identically 0. It's a perfectly believable conjecture. That last one who jumped on it was Yuri Bilou from Bordeaux, and so he got to know about it. He wrote to me immediately that he can prove it. Then I saw him in the afternoon. He said that no, that there was a mistake. But then it happened, I think, twice during my stay in Bordeaux. And then, I don't know, a couple of months ago, he wrote to me that one of his colleagues in Russia proved it. Unfortunately, I forgot his name. But then again, the details were wrong. So it's. I am sorry. That's a bad habit not to say the names.
Can I understand the statement?
Yeah.
Linear combinations of C tau, meaning for different tau.
You have finite number of long vectors.
Right.
And you want that in each row, you want to each of them you want to put rational number, so that in each of these infinite number of rows, you get 0. And that this polynomial somehow seemingly are independent.
Right.
So
For a given n.
Given n.
Yeah.
So for the columns are indexed by partitions of n.
Do you have a candidate for the set of linear combinations, or they are just a huge number, you don't find them easily?
I say that there is no non-trivial. I say that only the conjecture is that there is only trivial linear combination which is identically 0. And that conjecture would imply that this Q dichromate is as strong as U polynomial or U function.
Sorry, I didn't understand. You use the same rational number for each column, right? You take just.
You have this one column 1 alpha 1, second column alpha 2. But for each entry of the it's a linear combination of the columns of these vectors.
Because you have these vectors C of tau, and you would like to say
It's like vectors.
Sum of alpha tau. Well, easiest way to say it is that for a given n, all of the C of tau's are linearly independent over the rationals.
Yes, yes. Well, but there is if it will be finite dimension. Yes.
And you want the result to vanish identically in Q, right?
Yes, as a polynomial. Yes, yes.
Oh, as polynomials.
Yes, yes. It's funny. I like the conjecture. I think it looks to me kind of basic statement about partitions of numbers. There is the last aspect of this zeta function which I wanted to mention, and it's related to async problem. So I hope if you allow me 5 more minutes, it is that it's back to this non-commutativity. So here is a solution to 2-dimensional async problem due to Feynman, Potts, Sherman, and Ward. Well, I put them alphabetically, but the history is that Potts and Ward, no, Katz. Oh, I made a mistake. Sorry, not Potts, Katz and Ward. Katz and Ward showed that, or claimed that async 2-dimensional async partition function, so async for square grid, is equal to certain square root of certain determinant. It had complex entries, and their justification or their proof was wrong, but the statement was correct, and Feynman designed a nice way to prove it, but did not prove it. But then Sherman proved this, let's say, the formula of Feynman. All this happened in the end of 50s, and so what is the formula? So this is the statement which was conjectured by Feynman and proved by Sherman. So what do? You associate variables to each edges, and here you do it in this way as I described. So you have undirected graph. So to each edge you put variable, and that variable is also a variable which you associated with any orientation of that edge. All right. So you take product overall directed edges in the aperiodic closed walk, which is really that prime reduced cycle in the first slide, and well, it lives in the plane. So it's a kind of closed curve in the plane. It has a rotation. So we put -1 to the rotation. And well, this is additive, so it can be split into transitions between consecutive directed edges of the closed walk. So that's just this is a side remark. So this Feynman conjecture, if you wish to call it conjecture, which was proved by Sherman, is that the Ising partition, this is like the high temperature expansion of Ising partition function. It's a generating function of even subgraphs of the graph. G planar can be written as product overall of 1 minus WP. So where P here is this kind of strange bracket, it is that it's an equivalence class. Each equivalence class has two elements. I don't distinguish between going. So if you have a closed walk, there are two opposite ways of going through it, right? Which so far we distinguished, but here we don't distinguish, right? So the equivalence is up to the orientation of walking through the closed walk. So each equivalence class has exactly two elements. So this was proved by Sherman, and this really, because exactly the rotation can be split, this by theorem of Bass means that E square, this Ising partition function, can be written as determinant, right?
The certain P is a cyclic.
This E is Ising partition.
Gamma.
The P in the theorem.
The P is a gamma.
P is gamma in the first slide. It's aperiodic. It's this prime reduced cycle.
Aperiodic.
Yes, aperiodic. Yes.
Aperiodic is the same as prime, right?
Prime, yes. Prime is aperiodic, yes. So, so here this is the transition matrix of between edges, but it contains this rotation contribution, right? So that's of complex number.
Because the Bass, I mean, you showed the Bass theorem where T was just 1 if it's an allowed transition and 0 otherwise.
Yes.
But in fact, you
yes.
can put arbitrary
Yes.
weights in there
Yes.
and then
Yes.
get.
That is this Foata-Zellberger approach as arbitrary.
Right, and then you'll get
Yeah.
the sum over
Yeah.
those.
Yeah.
In Bass theorem, they are not necessarily aperiodic. In Bass theorem, the closed walk is not necessarily aperiodic.
It's prime. Prime
I mean, only you.
is aperiodic. Prime.
Is aperiodic the same?
Yeah, prime is that it's not power of smaller. It's not a non-trivial power, and that is the same as aperiodic.
It's prime. I confused.
Yeah, sorry.
Okay.
No, it's in fact here I in purpose put because this is how it's called in physics literature, but in math literature it's different. So there are two expressions which somehow there is of course this Pfaffian method to get the Ising partition function, and then this method So that means that this one Pfaffian, which is square root of one determinant, is equal to square root of another determinant. And there would be a nice, I think it would maybe interesting and enlightening to have a combinatorial proof of this identity, or what that means.
Well, this is also traditional, isn't it? It's not mysterious.
No, it's not mysterious. It's, well, you have equality of two square roots of determinant,
but it is
but there is no combinatorial proof of it.
Let me just expand that.
Well, unless you prove both things.
Let me expand on why it's mysterious. The T tilde in this Cotsword approach is a matrix whose rows and columns are indexed by directed edges of the original graph G, right? And then that approach gives square root of a determinant, and then there's actually some subtlety in figuring out which square root.
I don't see, for instance, I don't see a direct proof of this.
Well, let me just finish. The Pfaffian comes from a different approach to solving the Ising model. You take the Ising model on a graph G, and you map it on to a Deimer model or perfect matchings on some decorated version of G.
That's right.
Which is not G itself. And then you apply the Pfaffian method to that. And so it's not surprising that the Ising model is the Pfaffian of a matrix, but it's not a matrix living on the original graph. It's a matrix living on some bigger decorated graph.
And this is
But the combinatorial bijection is easy nonetheless.
no. So then, if you explain to me, I would be extremely glad. I don't know it.
I'm sorry, the bijection between Eulerian graphs on Eulerian subgraphs of G and that perfect matching.
And Dimers on the
That's
decorated. That
Right.
one is clear.
But still,
That is easy, but this is a different question.
But I'd like to see it at a
Well,
purely
from
algebraic.
Eulerian to square root of that is the proof. You cannot.
Yeah, but this is a different matrix. This is not this matrix AD.
The point
This
is
has
where
this has complex numbers. This has the rotation.
And the point is where these matrices live.
Yeah.
It's most natural to solve the Ising model on a graph G by writing a Pfaffian or determinant.
We can
living on
speak
G.
about it.
Vertices are edges.
Let me say, because there is one last thing which I wanted to say, and it is that it's kind of nice, this proof of Sherman of this statement. And it's one part is kind of elementary, but one part is it's non-trivial in the sense that it contains width identity. It's a nice statement from combinatorial group theory. Here is the statement that's needed to prove this conjecture of Feynman, and there does so Sherman wanted to avoid it. It doesn't. It really is there kind of very naturally, and again. I would like to, and don't understand yet, how this width identity is related with the Bass theorem and McMahon-Master theorem. And that, again, if we figure it out, there is a price for it, because that this width identity is somehow a basic tool in a different world. So somehow the understanding of it, let's say, a non-commutative analog of it can be extremely useful to other subjects. That's it. Thank you for your attention.
Martin, this thing at the end, if you take the reciprocal of both sides, doesn't that just come down to the Lindenward unique decomposition of...
I would love to see it. I don't know.
I think that's exactly the statement of it, because these
Please
components...
explain. I would love to hear. That would be great. That would be extreme. I would love to see it in this way. So
That was a question. not
There
an
doesn't
answer.
seem to be any ordering here.
you have,
Just say X, well, let's talk about it later. I'll do it on film.
there is no order, but it may be this kind of thing. But well, that's. Please, if you see it, please explain it to me.
To me, a lattice relation, like if you have the lattice of all n to the k, n where n are integers, and you are doing kind of the transform of 1 minus 1 on the atoms and everything 0,
Well, what it is useful, extremely useful in discounting, because it says that basically all this, in discounting you get some alternating sum, and that says that all terms aside of these simple guys disappear. So they struggled with, so there is actually the original paper of Sherman is nice also historically. He writes that Selberg has some, so Sherman made his proof and boiled everything into something which he called lemma on coin arrangements, and then he said that Selberg have a proof of it, and that it's related to this width identity, and he tried to prove it independently, and that proof was wrong, which, but in the end, I don't think that it's probably this lemma on coin arrangement is equivalent to width identity. I think it can be easily proven using width identity.
I have an idea of if you take the inverse of everything on the left and right, and take non-commutative variables.
Let's
then you get the free monoid, and then on the left you get what my good master Schutzenberger called factorization of free monoid.
Yeah.
And then like commuting variable, so you get the width.
Yeah. That would be great. That would be great. In fact, Schutzenberger.
Yes, in fact, I think Schutzenberger told me that in the Sherman proof there was a mistake.
Yeah.
And I think they make a joint paper to fill up in the 50.
That I did not see. So Schutzenberger, yes, please.
The Bass theorem. I see it instead of taking a product determinant, I call it determinant, take everything the inverse. The inverse of the determinant of your transition matrix on NG is going to be heaps of something.
Yes, exactly. That's why I, yes.
So it's a question of heaps.
Yes,
Maclaurin's
yes.
theorem now, I have shown very quickly in my talk in 10 seconds.
Yes.
Maclaurin's theorem, in fact, it's exactly, the determinant is cycle, 2 by 2
Yes.
square. The inverse is heaps of cycles.
Yes.
And the flow, you have just a flow, you have heaps of edges with,
Yes.
and there is a bijection between heaps of cycle and flow. It's easy.
Yeah, yeah. So that actually there's
Everything
heaps,
must be-
yes,
so
yes.
everything must be, as soon as you have the determinant, take the inverse, and working with heaps is more easier than just working. Because the Bass theorem, there is cancellation, everything, and in heaps there is no more.
Actually, your lecture was a motivation why I decided to speak about this zeta function.
Fouatta gave a proof of,
Yes.
20 years ago, we reproved all the linear algebra theorem, Hamilton, inverse.
Yes.
So there is a proof of Jacobi theorem, the one expansion,
Yes.
or something. So he also gave a proof, complicated with Lindon word, everything. And in fact, with Hips, Jacobi, you don't need Lindon.
Yeah,
Because
perfect.
Lindon
Yes.
word is a specific representative of circular word.
Yes.
And the notion of factorization of free monoid that I was talking about, it's any word can be decomposed into a sequence of decreasing words. Lindon word is a specific example. You have the whole basis, this is basis of Lie algebra. You have whole, so you have all kind of.
Yeah.
But in fact, it's circular word up to primitive.
Oh,
so this is my
please show me. I will, if you show me how weight is related to Bass or this Lindon unique factor, I would love to see it, because I have strong feeling that really it belongs to that word, and I cannot put it there.
David Rich told me also that I should use this tool of heaps of orient for the easing model to do something.
Yeah.
You have some ideas that just
Perfect. Let's speak about it. Very good.
not to stay on the floor level. As soon as you have a Bass, then take the inverse and you have everything.
Yeah, let's speak about it. Very good. Thank you.